In this research paper titled Syntactic and Semantic Control of Large Language Models via Sequential Monte Carlo, the authors explore ways to guide language models to generate text that meets specific constraints, such as syntactic rules or semantic meanings. This is crucial for applications like writing code, converting text to SQL queries, inferring goals from descriptions, or even synthesizing molecules in chemistry. The core idea is to make language models more precise and efficient by incorporating these constraints during the generation process. To understand this, let's start with the problem. Language models, like those based on transformers, typically generate text by predicting the next word based on what's come before, following a probability distribution. But often, we need the output to satisfy certain conditions. For example, in code generation, you might want the code to be syntactically correct, pass type checks, or produce the right output for a test case. These conditions can vary. They might be quick to check, like basic syntax, or more complex, like running a simulation. The authors frame this as a probabilistic problem. Imagine you have a base language model that gives a prior distribution over possible sequences of text. Then, you add constraints, which they represent as potential functions. These functions score how well a sequence meets the criteria. The goal is to sample from a new distribution that combines the language model's probabilities with these constraint scores. This is like a posterior distribution in Bayesian terms, where the prior is the language model's output, and the likelihood comes from the constraints. However, calculating this exactly is impossible for most cases because the distributions can be very complex, and normalizing them requires computing an intractable constant. That's where Sequential Monte Carlo, or SMC, comes in. SMC is a method from statistics that approximates complex distributions by using a series of weighted samples. In this context, it's adapted for sequential data, like text generation, where decisions are made one token at a time. Here's how it works in their framework. Instead of generating a full sequence and then checking it, SMC builds the sequence step by step. At each step, it maintains a set of partial sequences or particles, each with a weight that reflects how well it matches the constraints so far. The algorithm resamples these particles based on their weights, focusing computational resources on the most promising ones. This allows for efficient adaptation. If a partial sequence looks bad early on, it can be discarded without wasting effort on completing it. One key advantage is flexibility. You can plug in different types of constraints at inference time, without retraining the model. For instance, you could use cheap checks like linting for code, or more expensive ones like running simulations. SMC handles both hard constraints, which must be met exactly, and soft ones, which are scored on a scale. It also reallocates resources dynamically, spending more time on uncertain parts of the generation process. To evaluate this, the authors compare their SMC approach to other methods on 4 challenging domains. First, Python code generation for data science tasks, where the model has to write code that processes data correctly. Second, text-to-SQL, converting natural language questions into SQL queries that work on a database. Third, goal inference, like predicting actions in a scenario based on described objectives. And fourth, molecule synthesis, generating chemical structures that meet specific properties. In their experiments, they show that even small, open-source language models using SMC outperform much larger models, some over 8 times bigger, and even closed-source, fine-tuned ones. This is impressive because it means you don't need massive resources to get high-quality results. The improvements come from better approximating the true posterior distribution, meaning the generated text is more likely to satisfy the constraints while still being coherent. They also highlight that SMC has little overhead, so it doesn't slow down generation much compared to baseline methods. For example, compared to locally constrained decoding, which adjusts probabilities at each token but might not handle global constraints well, SMC provides a more accurate global picture. And unlike sample re-ranking, where you generate many full sequences and then pick the best, SMC avoids generating invalid ones from the start, saving time and computation. This work builds on a previous framework by Liu and colleagues from 2023, and it integrates with a language model probabilistic programming language. This makes it user-friendly. You can program your own constraints and apply SMC easily. They've even provided a GitHub repository for others to use and extend this system. Overall, by leveraging sequential Monte Carlo, this approach offers a powerful, efficient way to control language models, making them more reliable for real-world applications where precision matters.